Solar Power Tower. Explanation of Solar Power Tower. The Solar Power Tower, also known as central tower, power plants or heliostat power plants or power towers, is a type of solar furnace using a tower to receive the focused sunlight. It uses an array of flat, movable mirrors to focus the sun's rays upon a collector tower. Classification of Solar Power Tower. First-generation technologies are most competitive in locations with abundant resources. Their future depends on exploration of available resource potential, particularly in developing countries, and on overcoming challenges related to environment and social acceptance. Example: hydroelectric plants, geothermal power plants, and biomass briquettes. Second-generation technologies are said to be the future of power generation and is fast catching up, but the market for these sources are limited to only a few countries. Example: solar heating systems, use of ethanol, etc. Third-generation technologies are not yet widely demonstrated or commercialized. They are on the horizon and may have potential comparable to other renewable energy technologies, but still depend on attracting sufficient attention and R&D funding. Solar Power Towers. Solar Tower. Solar power towers, also known as concentrated solar power, CSP, towers generate electric power from sunlight by focusing concentrated solar radiation on tower-mounted heat exchangers. The system uses hundreds to thousands of sun-tracking mirrors, called heliostats, to reflect the incident sunlight onto the receiver. These plants are best suited for utility-scale applications in the 30 to 400 MW range. The limited supply of fossil hydrocarbon resources and the negative impact of CO2 emissions on the global environment dictate the increasing usage of renewable energy sources. Concentrated solar power, CSP, is the most likely candidate for providing the majority of this renewable energy, because it is amongst the most cost-effective renewable electricity technologies, and because its supply is not restricted if the energy generated is transported from the world's solar belt to the population centers. This energy is then passed either to the storage or to power conversion systems, which convert the thermal energy into electricity. Power tower systems usually achieves concentration ratios of 300 to 1500, can operate at temperatures up to 1500 OC. Heliostats. Heliostats are reflective surfaces or mirrors which track the sun's rays and reflect it onto the central receiver. Relatively few heliostats have been manufactured to date, and their cost is high. As the demand for solar power increases, heliostat mass production methods will be developed that will significantly reduce their cost. Prices are a strong function of annual production rate. Solar power towers. Since the heliostat field represents the largest single capital investment in a power tower plant, advancements in technology are needed to improve the ability to manufacture, reduce costs, and increase the service life of heliostats. In particular, a lower-cost azimuth drive system is needed. Central receiver. Central receiver, or power tower, systems use a field of distributed mirrors, heliostats, that individually track the sun and focus the sunlight on the top of a tower. By concentrating the sunlight 600 to 1000 times, they achieve temperatures from 800 degrees Celsius to well over 1000 degrees Celsius. The central receiver is also called high-tech heat exchanger, which sits atop a tower. The central receiver heats molten salt at around 250 degrees Celsius, pumped from a cold storage tank, to 565 degrees Celsius, where it flows to a hot tank for storage. When the grid load dispatcher decides electricity is needed from the plant, hot salt is pumped to a steam generating system that produces superheated steam for a turbine/generator. The salt then is returned to the cold tank, where it is stored and eventually reheated in the receiver to complete the cycle. Smaller, simpler receivers are needed to improve efficiency and reduce maintenance. Molten salt or molten salt storage system. Molten nitrate salt, though an excellent thermal storage medium, can be a troublesome fluid to deal with because of its relatively high freezing point, 220 OC/428 degree F. To keep the salt molten, a fairly complex heat trace system must be employed. Heat tracing is composed of electric wires attached to the outside surface of pipes. Pipes are kept warm by way of resistance heating. Problems were experienced during the startup of Solar 2 due to the improper installation of the heat trace. Though this problem has been addressed and corrected, research is needed to reduce the reliance on heat tracing in the plant. Steam generator or turbines. The steam generator design selected for the Solar 2 project is completely different than the prototype tested at Sandia Laboratories during the technology development activity of the 1980s for Solar 1 because of change in heat transfer fluid. The recirculating drum type system tested at Sandia performed well. However, at Solar 2, a kettle boiler design was selected in an attempt to reduce cost. Significant problems have been encountered with this new system during the startup phase at Solar 2, requiring a redesign in many areas. Depending on the success of implementing the design changes, it was considered appropriate to re-evaluate the optimum steam generator design before proceeding to the first commercial plant. Solar Power Tower Working Country. 1. United States. 2. Germany. 3. Turkey. 4. South Africa. 5. Israel. 6. Spain.